Now we are discussing about bitwise logical operator complement. When I use this similar to, or you can call it as a slide, when I use this operator with 2, then it will complement the binary equivalent number of that 2. So what is the binary equivalent number of 2? So I am representing, because we have to take at least 1 byte to represent this 2. In the 1 byte we are having 8 bits. I am representing this 2 by using 8 bits, 0, 0, 0, 0 and so on, 1, 0. Now when I complement this 2, what it means? We are making ones in the place of zeros, and we are converting ones to zeros. So we are converting zeros to ones, and we are converting ones to zeros. That's how this is simply a complement of, if I am taking 1 1 0, what is the complement of this? 0 0 1. Here instead of 1 I have taken 0, instead of 0 I have taken 1. Simply I have complemented. Wherever the 1 is there in the original number, we are replacing with 0. Wherever 0 is there in the original number, we are replacing it with the 1. So this is the complement. But now the scenario is, if we look at this number, this is a big number that is appearing to us. That might be a larger number. But the computer does not give the complement of 2 as this big number. Instead of that, it is giving the complement of 2 as a -3. How it is giving -3? We are seeing in front of us, which is a big number, which is having ones in the place of 2 to the power even 7 also in the last bit of this byte also 1 is there. How the computer is giving the complement of 2 as -3 in the Python? For that, first we will know what is, first we will discuss about what is 3. 3 is nothing but 0 0. All remaining digits are zeros, and the last 2 digits are 1. Now when we are performing the ones complement to this number, ones complement means simply we are performing the complement only. When we are performing the ones complement, all the zeros are replaced with ones and ones are replaced with the zeros. Now when I am performing the twos complement, just I am adding a 1 to the ones complement, then it is twos complement of 3. So this twos complement of 3 is matching with the bitwise logical complement of 2. See, so bitwise logical complement of 2 is matching with the 3's twos complement. So the computer calls this 3's twos complement as a -3. So as for the computer understanding, whenever we tell a number 4's twos complement, computer understand it is -4. So computer does not know what is -4 in reality. When we are telling -5, the computer understands it as a twos complement of 5. Similarly, because this number is same as 2's complement of 3, so this will be represented by the computer as -3, because the last bit is a signed bit. So when after seeing this signed bit, the computer is representing the binary equivalent of bitwise logical complement of 2 is represented by -3. Similarly, when we give the number 5, the bitwise logical complement of 5 is -6. Means the bitwise logical complement of 5 is exactly same as the 2's complement of 6. So that's why the computer is representing the bitwise logical complement of 5 as -6. Now we will check in the ideally. You observe here, we are giving bitwise complement of 2, it is -3. So the bitwise complement of 2 is equivalent to the 2's complement of 3. Now I am giving some big number, some 989. Sorry, I have not taken the bitwise logical complement. Okay. So bitwise, I am performing the complement by using bitwise logical operator. So now you can observe this is minus 990. So this is the complement of 989. So 989 complement is exactly same as 2's complement of 990. If I give another number, some 1000, so the complement of the 1000, so when I am taking the bitwise logical operator, so the bitwise logical complement of 1000 is the same as 2's complement of minus 1001. This is how we perform the bitwise logical complement.